So the concept behind uh, the drive electronics is that we have this piezoelectric device that warms up while it's operating. The temperature shifts cause a shift in resonant frequency. Um, by monitoring the voltage and current and the temperature, we should be able to construct an intelligent system that will track um, the point just off resonance that we seek and track it with regards to temperature. In other words, adjust it based on temperature and on the voltage and current waveforms we're seeing that indicate the reactance and the oscillation mode it's in. If we can do that, then we can provide a steady signal instead of a swept signal at frequency and accommodate the high Q of the system. We are working on the third iteration of the electronics. We learned a lot in each step. The block diagram here explains kind of how the hardware is constructed. There's drive logic, including a DSP and all the associated logic required. A bridge drive, a little bit of inductive filtering, a little bit of filtering in order to get rid of the high frequency switching noises and provide the drive to the stack. We have voltage sensing and current sensing on the stack, on the device under test. And we also have strain gauge input and other feedback sources available in the electronics hardware so that we can take data from several different sources to help control the center frequency, the power output, and waveform, etc. The software that drives it allows you to construct the waveform, not just the fundamental, but the harmonics, and set their amplitude and phase. You can also create a waveform mathematically in Excel or some other spreadsheet and or any other tool and save it as a comma delimited file, CSV file, and load it into the system and use that waveform. Once a waveform is generated or loaded into the system, we then have a page that allows us to run the waveform. The implementation on this example page here is with no sweep. It has a 2-second pause before you start. It has a soft start. Instead of just switching it on hard, we always turn it on at 0 crossing, and we bring the amplitude up a little bit slowly so that we don't introduce too much jerk in the system, and we have a smooth startup. And then we have a signal duration that we can set, and then we have a soft stop, and and you can insert a pause after the test, and you can also tell it how many iterations you want of that specific test. So once we get it running correctly, this is the ideal way to test it with long durations in the signal. We do have the option with this system of running it in sweep mode. And in sweep mode, you can specify all the same things you could in steady state mode. And you specify the sweep duration in seconds and the sweep range in kilohertz or hertz. That gives you a lot of precision in finding the fundamental and the harmonics that help you know exactly what the operating frequency of the device under test is. I'll show you a couple of pictures. This is the first generation of the electronic stack up. There's a control board. there's a driver board underneath with power conversion and the 8-bridge high voltage drive and the logic board that creates the waveform. This is the second generation, same general configuration. And the third generation, I received the board day before yesterday, and we were building it now. So we'll keep you guys updated. That's all I have.
Thank you very much.
Thank you. That's awesome. Okay. Well, we now actually, if there's any quick comments for Chip, any other questions? Because now we're cutting into our coffee time. So I'd recommend.
I'm sorry, I do have one quick question.
Go for it,
for
Ron.
Chip. I mean, is the objective of this to keep the device running at positive thrust at that high thrust level instead of sweeping through the thrust, the thrust profile? Is that the objective of the electronics?
That is one very important objective. Other objectives include the ability to systematically profile the devices and understand them better. But the primary objective is, as you mentioned, yes.
And Jim, do you have a comment on that objective and where we might be toward achieving that?
Do I have a comment?
Yeah, do you?
We're waiting. We're waiting
Okay.
with bated breath.
Okay,
For Chip's-
all right. No,
Chip's
I mean, that's
amplifier.
obviously that's obviously going to be very,
Yeah.
very
There
cool.
are two ways, Ron, that this can be run. One is steady frequency for some duty cycle. And if you've got an amplifier that will track the resonance properly and all that, that's the preferable way to do it. The other is to chirp the signal. That is to say, use the soft on or soft off as Chip's talking about. It turns out that the math of these things tells you that a switching transient will produce even more thrust than steady running at a constant frequency under less than optimal circumstances. That was what was presented at Estes Park 2 years ago, I guess it was. Chirp signals, was that 2 years ago, Heidi, or was that 4 years ago? Anyway, there are two ways of doing it. One's chirping, the other is duty cycle, 10%, 20% duty cycle, constant frequency. And Chip's amplifier will hopefully be able to do both. As a matter of fact, Max Cummins' comment was to Heidi, I don't know if you saw it, if it came up, he said, have you been using the signal processing software that I wrote for you? He wrote us a chirping program, okay? It's intended for use with this sort of system. And the answer, Max, if you're still on, is no, we haven't used it yet, but we're waiting.
Well, I'm here and yeah, give it a shot.
We're waiting to give it a shot, Max. Your work's not going to go in vain.
That's good.
I have a question, George, again. That's great, Chip. Looking forward to that. It's pretty complicated too. I'm wondering whether it's inherent in the piezoelectric response that there is a second harmonic. And the reason I'm asking, is there any control experiment that can be designed that suppresses the second harmonic?
Yeah, you could, George, the answer to that one is simple. Most of them don't give you much of a second harmonic. The third harmonic is the first dominant harmonic. Yes, we have APC stacks. We have tried to work this way, with single frequency excitation, and you don't see much of a second harmonic at all.
And when you don't see a second harmonic, you don't
see a thrust signal.
Okay. I'd like to see those. That's useful. Thank you.
I'll
And I
tell
gotta
you what,
go, unfortunately.
we'll send you an APC stack along with the other stuff.
Question for you guys, if you got another moment here.
Yeah.
Okay.
Okay, so first one is it necessary to use brass, or would a, say, more rigid material that could generate a sharper second harmonic maybe be more ideal?
Could you make the reaction mass out of something other than brass, which is very easy to machine?
Right,
Yes.
so is that the primary reason, is that it was easy to machine?
It was easy to machine and it's cheap.
Okay.
We actually have a piece of, what is it, tungsten?
Tungsten.
Al?
Mm-hmm.
Tungsten?
Wow. Yeah,
Yeah,
that would be a great test for
Really, really nasty to machine though. The
We
machine is
haven't-
not happy.
I took a piece of tungsten and took a Dremel tool to it with a diamond disc, and it basically destroyed my disc and did very little to the tungsten. But so that's pretty much.
Yeah.
The second question I had was regarding springs, tensioning, and keeping this thing in the center. Has anybody ever tried to use magnetics on a second set of ears sticking out? You couldn't put magnets next to the bearings because they're very magnetically sensitive, as I've found out in prior tests. But you could
Yes.
it's centered to put some magnets between those spaces, maybe with the second set of ears. They wouldn't really need to be
Instead of using springs. Yeah.
right.
Yeah,
Then you
some
really
sort of-
use friction.
Yes,
way.
your suggestion that something other than material springs as a way of centering the device. The centering device is the thing that transfers the force from the device that's being generated,
Right,
okay,
but the
to the
magnet-
rest of the thing. So you have to have some sort of centering system to
Right.
see a
That's what I'm
thrust.
saying, is the magnets would still transfer the force. I mean, they're still exerting forces upon
Yes.
each other.
Yes, yes, yeah. As long as you're using rods, you can get away with it if you can figure out how to mount them in such a way that it doesn't screw up the acoustic behavior of the reaction mass. Okay, if you compress the ears with rubber O-rings, even light compression is enough to disrupt the second harmonic and the signal goes away.
Yeah, that makes sense too with my test with acoustic levitation and using PZTs. They are very, very sensitive when you get them in their harmonic resonance to anything that damps them. And then the
Yes.
third and last question that I had was, as far as scalability, I understand that because the ceramics are poor heat conductors, that making them larger makes the difficulty of removing the heat even more complicated. But, say that copper plates were used in between, or perhaps some kind of cooling system were implemented to run down the center where the bore is, just to help
We have
things
been fooling around with cooling ideas, yes.
But
The
are
obvious way,
scalable? Can you make
the
them bigger?
obvious way to extract the heat from the system is through the electrodes. And we're using brass electrodes instead of copper, because if you use copper electrodes, which are much more thermally conductive, not only do you conduct the heat away from the stack, you also conduct the heat when you're soldering them into the stack, and you run the risk of depolling the stack. In which case,
That's a good point. I have a special soldering system that I designed for that, which has a dual carbon electrode, which can heat very, very quickly a small area of copper without transferring into sensitive materials like the
oh,
PZ.
really?
Yeah, it
You're
works really
serious about this stuff.
Oh boy, I've been doing it for 21 years. Actually, I started when I was 13.
Wow.
Yes,
Mark,
And you guys are pretty much, like my heroes. So I can only try to express how awesome this actually is to have the opportunity.
we have clay feet, you should understand.
yes.
Basically,
I respect tremendously the amount of effort that goes into all of this research. It is such a labor of love, and its returns on investment are very, very small. So you have to have the passion for it and be self-motivated, because heaven knows nobody else is going to drive you there.
By the
Yeah.
way, Mark and Jeremiah, this is Paul.
Hey, Paul.
You asked a question this morning about whether the test articles could generate a gravitational effect, lose weight when
Yes.
they're active.
We were
Are you
curious
familiar
about
with the
Thomas
the entire Mach effect derivation, the first, second, and third terms?
No, I'll be honest in saying that I am not that well trained on the mathematics. I'm a self-taught individual, so I've not had an opportunity to really learn the more complicated stuff. I've just been basically engineering and building this stuff. That's where I come into specialty, is high voltage, very high voltages, upwards of a megavolts in some of my tests, very high currents, upwards of a 1.5 mega amps, and then I just build. But I struggle with mathematics in some cases, so I do apologize.
Okay. Well, just for an FYI, Jim has been concentrating on his first term of his, what he calls the impulse drive term of his Mach effect equation. But if you look at the second term, that's a very interesting term that I think there's a 2002 report you need to check out from Jim. And it will reveal some very interesting test results.
I would
And I'll leave
certainly
it at that.
look for that.
it's,
So if I were
it's
to
in,
find
it's in, it's in chapter 4 of Making Starships and Stargates, the science of interstellar propulsion and absurdly benign wormholes.
Mhm.
Springer,
Thank you, Jim.
2013.
I'll go ahead and get a copy of that for myself.
Yeah,
Okay,
worth the
guys, I
read.
think I'm going to have to stop you there because we're running over time. We've already missed our coffee break. Too bad. We're going to have to, go into Jeff Greason's talk now.
Yes.
And,